This is a concept kids struggle with, and this is going to be a bunch of marks on your test if that's what you care about. This is going to be an important concept to wrap our brain around the rest of the unit. I want to talk about electric field. First of all, the gravitational field reflects the effects that a mass has on space around it. Caleb, if I put a big mass in outer space somewhere, it is going to send out, like the invisible tentacles of an octopus in all directions, a gravitational field. And that gravitational field is going to sit there. As soon as another mass comes along and enters that gravitational field, that other mass is going to feel a force. What force? Force of gravity. How do I calculate that force? The little mass times the strength of the gravitational field right there. That's how I taught you gravity in Physics 11, and we got away with it because in Physics 11 we never left the Earth, so little g was always 9.8. Or you could think about it as big G, big M, little m over r squared. Two ways to calculate gravity, yes? And Max, what that really means, I guess, is that little g and this big G, big M over r squared are the same thing because there's the little m that they're multiplying onto to get the same answer. So what we had last unit, Allie, was two ways to find gravitational field strength, two ways to define it. First of all, we started out with the force of gravity, big G, big M, little m over r squared. And then we actually defined universal gravitational field strength. We said that was big G, big M over r squared, no little m. I did not give you that equation on your formula sheet on purpose. What I did give you was gravity field as a ratio. I said, well, it's also Fg over little m. I got the g by itself in this equation right here, but can you see how by doing that, I'm actually kind of giving you that, because if you cancel out the little m, you get that. We had two different ways to think about finding gravitational field. But if we knew the planet that was causing the field, we could use this. If we didn't know the planet, but we could feel the force that was tugging on a mass, we could use this. What were the units? Yep. Or? Okay. Are you ready for your spoiler alert? Don't write this next bit down. We're going to write it in the notes on the next page. But for what it's worth, electric field, I can find it in two ways. We're going to use a capital E for electric field. Lowercase e is an electron, and it's also a number. Those either taken pre-calc 12, so that's electric field. And one way to find it is going to be electric force divided by little q. Because Q in electric charge is going to behave just like mass does in gravity. Or another way to find it is going to be little k big Q over r squared. Looks kind of like that one. That's sort of the punchline we're going to get to. Oh, and you know what? There's going to be two different units for that one as well. First of all, let's stick with gravity. Example, well, Naomi, what does example A want me to find? What does example B want me to find? Same thing. I'm going to go like that, and I'm going to do A here. I'm going to do B here. And for both of them, I guess it's going to be find little g, because that's our symbol for gravitational field strength. Front row Camille, how will I find little g in part A? Well, first of all, what's this? What are the units next to this 8.38 times 10 to the 6th? Which one of these two definitions for gravitational field has something that I would measure in meters in? That one. What's big M? The planet that's causing the gravitational field, and in this case they told me Earth. If they hadn't told me Earth, they'd have to give me the mass, big M, of the planet. Anyways, it's going to be big G, 5.98 times 10 to the 24th, all over. This 8.36 times 10 to the 6 meters, it's from the Earth's center, so it is a radius. .38 times 10 to the 6, what, Allie? What, Allie? What, Allie? What, Allie? Okay. What do you get? I hope I'm remembering yours correct. It might have been someone else, but I think it was you. I apologize if I was wrong. Oh, first of all, I know it's going to be less than 9.8. Got to have a bit of a built-in error check here. 5.68? Clearly, Allie, I was mistaken. Adam, R what? R what? R what? Units, newtons per kilogram. Is it 5.68 or is it 5.67? You're using the constant button, right? Or you're not? Okay, never mind. Should be. Is it 5.68? Okay. What about here? Well, Alexis, what are the units next to this 750? Which one of these two has a force in it? This one. Yes? Has F. You know, you can look at your own sheet. Oh, yeah. The gravity field as a ratio. It's going to be the force of gravity divided by the mass at that location. I don't know what planet is sending out this gravity field. They haven't given me big M. But I don't need a calculator for this either. What is the force of gravity at this location, Alexis? Force? What's the mass? In your head? This is some strange mystery planet somewhere. Clearly larger than Earth. So that's a quick brush up on gravity field. Now there's a bit of a problem that we ran into with gravity field, and a couple of you did this on the test. Because gravity field starts with F, some of you found a force. It's not a force. And I had to give you 0 because I said find the gravitational field and you found a force in newtons. I'm glad you did that, and you may have done it correctly, but it's not what I asked for, and I can't even give you any part marks along the way. We're going to define electric field in a similar manner. If we have a planetary charge Q, a big charge, as soon as it exists, it is sending out, like the invisible tentacles of an octopus in all directions, an electric field. This is how it's able to exert what we called action at a distance. It's like that meter stick that I kept poking Naomi with. As soon as we put a small charge there, this charge is going to feel a force. What force? An electric force. How will you calculate it? Look up, look up. Everybody look up. Everyone look up. Keep looking up. Little q times E. Hey, doesn't that look an awful lot like mg? That's the electric force there. Charge times electric field gives you newtons. The same way mass times gravitational field gives you newtons. Oh, and it's also going to be K, big Q, little q over R squared. That's Coulomb's law that we did last lesson. Oh, Mr. Duick, I guess that means that another way to calculate electric field, those two things must be the same, because little q multiplying by the same thing gives you the same answer. So we're going to run into one problem, though. Lyle, like charges? Not only can the force be in that direction, it can also be in that direction. Unfortunately, unlike with gravity, stuff can fall up. We'll have to deal with that. In fact, unlike with gravity, we're going to have to define an electric field direction. We're going to have to we got to give it a direction. We're going to give you a rule for finding the direction. Gravity was out towards the center, but nothing fell up. Example 3 says, fill in the appropriate relationships. So we have the force of electricity, Coulomb's law, K, big Q, little q over R squared. It says, definition of electric field. I'll come to that in a second. But first of all, electric field as a ratio is the force at a location divided by the little charge at that location. This is the equivalent, don't write this down, this is the equivalent of little g equals the force of gravity divided by m. In fact, this is what gives us force of gravity, mg. Get the obvious one. The force between a charge when it's on an electric field is QE. That's the version of get the obvious one for electricity. And this would definitely be newtons per coulomb. It's a scalar equation. Even though I put vector symbols in there, this will give you the magnitude. We will have to figure out the direction of the electric field. How? I haven't taught you yet. Or the other version of electric field comes from the stuff that I circled. Electric field, if you know the big planet that's causing, the big planetary charge that's causing everything, is that one. KQ over what atom? Over what atom? Over what atom? Now, I'm not making fun of atom. Here's the problem we're going to run into. Look at your formula sheet. In fact, I'm going to go to a formula sheet right now. In this unit, one of the big problems is that everything looks alike. Let me show you what I mean. Here's electric force, KQ1, Q2 over R squared. Here's electric field, KQ over R squared. Here's potential energy, KQ1, Q2 over R. Here's voltage, KQ over R. Do you think it's easy to get the squareds and the not squareds mixed up? Yes. Do you think it's easy to get, oh, and by the way, just for giggles, force, field, electric field. It's really easy to get these mixed up. Can I give you a little bit of advice to most of you? This unit in particular, you don't want to try and cram all the homework in on the end and learn it on the fly. You want to keep up with the homework. If you try and do all the homework 2 or 3 days before the test, you will get all of these mixed up and you'll just bomb on the test. Because I'll say, find the electric field and you'll find the force. Or I'll say, find the electric, oh, by the way, potential energy, potential. So I'll say, find the potential, and you'll find the potential energy. And again, you may have found the potential energy correctly. Zero. That's not what I asked for. I can't even give you any part marks. So don't be that. Keep up with the homework. You know who you are. Definition of electric field. So the actual definition of electric field is this one. E equals KQ over R squared. It's this one down here. But because of that, Donald, you can also get, oh, it's the force of electricity, electric force divided by the charge at that location. What are the units for electric field? What were the units for gravitational field? Newtons per? So newtons per coulomb. Or, there is another one, but I can't tell you yet. No, it's not meters. No, it can't be an acceleration because it's not a mass, right? It'd only be an acceleration if this was a mass. Charge is not mass. It behaves mathematically the same way mass does for gravity as charge does for electric force, but they're different phenomena. By the way, I think actually on your formula sheet, correct me if I'm wrong, I put absolute value signs around that Q. Didn't? Yeah, we don't put negatives and positives into the actual equation. We'll use the negative or the positive to figure out the direction of the electric field. You're going to miss out, but good luck on your game. So many textbooks will give the electric field equation as K absolute value of Q over R squared. At a certain point in space, a negative 0.5, oh, what's that little funky symbol there mean? Micro. What does micro mean? I replaced that with a 10 to the. That's worth committing to memory, this unit, because you're going to be doing it on every question. It's on your formula sheet, by the way, in that metric chart. You'll see mu micro 10 to the negative 6. But this is one of the metric prefixes that's probably worth memorizing, at least for this unit. At a certain point in space, negative 0.5 microcoulomb test charge experiences a force of that towards the south. Find the magnitude of the electric field strength at this point. Hannah, what does this want me to find the magnitude of? What does B want me to find the magnitude of? Oh, Hannah, we have two versions of electric field. We have this one, E equals K big Q over R squared. And we have this one, E equals the electric force divided by little q at that location. Which one am I going to use for part A? Well, Hannah, what are the units next to this number? What do I measure in newtons? I'm looking for a word that starts with the letter F. Which one of these two has a force in it? This has a force in it? Which one of these two has a force in it? Yeah. Okay. The electric field is going to be F, and this is how you can figure out which one of these you're going to use. It's going to be 5.2 times 10 to the negative 4 divided by 0.5. We don't put the negative in. And then micro is just times 10 to the negative 6. Oh, I can probably do this in my head. 10.4, where do the zeros end up? 1040, I think. Yeah. So, since this is your brand new intro to electric fields will usually be in the thousands or tens of thousands or hundreds of thousands. If you get an electric field of 7, you've done it wrong. If you get an electric field of 0.05, not a chance. You've done it wrong. Also, the fact that electric fields are large just tells you electric force way bigger than gravitational force. So 1040 newtons per coulomb. B. Ooh, Hannah, what are the units next to this 0.450? The reason I ignored the charge, this is coulombs, they both have Q's in them, but one has an F in it, newtons, one has R squared in it, meters. So the fact that this is meters, I know to use the one with the atom R what? In it. What was K? No, what was K? 9 times 10 to the 9th? Much nicer than 6.67 times 10 to the negative 11, but that's the Coulomb's law constant. Big Q, 2.3 micro times 10 to the negative 6, all over 0.45. Don't forget the squared. I think you're going to get something in the 100,000s, but I can't do much more than that in my head. I might be wrong. 9 times 10 to the 9th times 2.3 times 10 to the negative 6 divided by 0.45. Don't forget the squared. Yeah, you get 102,000? I'll go 1.02 times 10 to the 5th newtons per coulomb. Now you'll notice I've been writing a vector symbol. I haven't given you a direction because this only asks for the magnitude. How do you get the direction? We have to define it. Next page. So I wrote here, the direction of the electric field, well, with gravity, it was never an issue. Down toward the center. With charges, like charges, and so stuff can fall up. So I did it in bold font and underlined. You're going to have to memorize this. Put a star next to this, whatever you need to do. This is how we determine the direction of the electric field. We say the direction of the electric field is the direction that a small positive test charge would want to move if it was placed there. We ask, if I put a positive there, which way would it move if it could? That's the direction of the electric field. So let me show you what I mean. Example 5a says, find the direction of the electric field at a point where a negative 0.5 microcoulomb test charge experiences a force towards the, is this charge negative or positive? The test charge is negative. So if a negative feels a force to the south, which way would a positive charge feel a force? If a negative charge feels a force to the south, which way would a positive charge feel a force? North. Which way is the electric field? Same answer. We ask, which way would a positive put right there want to move if it could? A tiny positive. How tiny? To be honest, so tiny it doesn't have its own electric field, because that would change the question. So it's really imaginary, but it's positive. I'm positive. And how we figure out which way the positive will want to move, we'll use like charges, unlike charges attract. So B says, find the direction of the electric field 0.45 meters to the right of this charge. So it wants us to find the electric field right there, direction. We found the magnitude. By the way, if you haven't noticed, these are the same two questions in example 4. We crunched the magnitudes in example 4. We didn't do the directions. The charge sitting right here, big Q, positive or negative? I might even put a big plus on there to remind myself of that. Okay, so at location X, which way would a positive want to move if it could? Left or right? Let me rephrase that. Left or right? Let me rephrase that. Left or right? Which way, Max?
Right.
Or you could say east. I don't care, but I'll figure it out. So what's the direction of electric field? We ask, which way would a positive want to move if it could? This is where my morning lesson, the computer crashed, so I'm going to pause here and hit save, so at least I have a lesson.